It seems like it's 10 a.m., so it's time to start. So, first things first, welcome everyone. My name is Grzegorz, and I'm really happy to be here again. We have not a lot of time, so let's go straight to the topic of today. So, the topic of today is Java 8. Wow, right? Java 8 has been around for quite a lot of time, quite long period of time. It got out in 2014, around February, I think. And it's been quite a hot topic for quite a while. So you might be surprised why we are still talking about Java 8. So the point for today is, you will see, some of you are already on Java 11, some of you are on Java 8, some of you earn a lot of money are still on Java 4. But the point of today is to show you that actually, besides major, let's say, big bang releases of Java with big, huge, and shiny new features, there are still a lot of small ones that's important to remember about. So Java 8 was a very special release. In 2014, we got, well, quite a lot of functional programming features introduced, which is something very new for Java. Because if you've been following the whole story, Java 8 was always like very radical OOP. You mean radical like Jeegonf kind of style. And I remember that long time ago that Mark Reinhold would keep mentioning that Java will never get lambda expressions because this is not how they imagine Java to look like. Well, but the community pressure and pressure from other languages like Scala and nowadays Kotlin forced them to adopt, introduce new features, adopt functional programming ideas. So Java 8 was very hot. Straight after that, Java 9 followed. So I remember that many people wanted to migrate as fast as possible to Java 8. But once Java 9 went out, Java 9 was all about modularity. And then it did not become that popular. And let's actually do a short test. So how many of you are actually on Java 11 or 12? Wow, that's quite a lot of you. How many of you are on Java 8? Yes, that's what I'm speaking about. Java 7? 6? Okay, sorry. So the point being, when I was asked, I was doing different talks about different subjects, but I would ask the same question. And the Java 9 adoption at that point, or Java 10, was very, very, very small. And actually, many people would claim that they don't need Java 9 at all. They don't need modularity. They don't need local variable type inference from JDK 10, or some other small features from JDK 11. So let's have a look at some scientific data, how the Java 9 adoption looks like. And it's been the case for a very long time, unfortunately. But my point for today is to convince you that there are many small things that went into Java that actually is worth considering important. Although they are not big and shiny, but can contribute to our development or our production stability a lot. So if you've been in Java world for a long time, you probably remember that the Java versions were released, well, not that often, okay? That would something that would happen every 4 or 5 years or even more. So most of us are likely to see, just a few Java versions in our lifetimes. But our kids probably will see like hundreds of them. That's because there was a huge change regarding how the Java is shipped right now. In the past, it was all about features. It was feature-driven. It means that, well, in Java 8, those were lambdas. So we waited many, many years till this one feature is polished and ready to ship. Then we waited quite a long time for Project Jigsaw, JPMS. And, well, there were some problems regarding when encountered during the development. So again, it would delay the release of Java 9, I think 2 years at that point, or around 18 months. And the point is that everyone noticed that this is not a great model, because, well, the whole Java 8, Java 9, Java 7 is not only about lambdas, Project Jigsaw, or strings in switch expressions. It's also about there's a lot of fixes coming to the Java virtual machine itself. There are fixes coming to APIs, or just small APIs that can make your life easier. So this is when they figured out that it's time to make a change. It's time to go to cadence-driven releases, which means that every 6 months we get a Java release, even if there's one feature, very small feature to be released, it still goes out. But what about another big feature, like for example, Project Valhalla? Well, if it's not ready, then it's not ready. The train started off. So this is how we can get quite a lot of small details, well, every 6 months. By the way, Java 12 is already out, if you don't remember. But an important thing to remember is that not all Java releases were made equal. Java 7, Java 8, Java 11, those were long-term releases, which means they'll be supported for 3 years. But Java 9, 10, 12, and everything till Java 17 are small feature releases which are short-lived. They will live only for 6 months, and after this they will not receive support. Which means that you can make a choice. You can, as Mark Reinhold would call it, it's a blue pill, red pill choice. So you can either go for stable, secure, long-term releases and migrate every 3 years, or just try to catch up with a Java train and migrate every 6 months. The choice is up to you. So we are done with the introduction. Let's go to actual, let's say, scenes of Java, Java 8, 9, and 10, actually. So the first issue is, well, it's very trivial, but it's very important to build suspension before other bugs that are coming. So, very simple scenario, conditional stream termination. Imagine that you have a simple list returning dates. But let's say those are dates of users getting registered over time. So we know that those dates will be, well, increasing, okay? Pretty much sorted in time. And our task is to just take all dates before certain date. And you can achieve this very easily because, well, we can use Stream API, leverage the declarative approach to, like, let's say, querying collections. And we say, give us all the dates, take all dates before whatever we are querying for, do something with that, and process them. And this will work correctly, obviously. But there's a small problem related to that. So it will work fine, but unfortunately, internally, Stream will evaluate all elements from that stream. Because there is no way to provide any form of information that, hey, after the first encounter of a mismatch regarding of an element that doesn't match the predicate past, can't just terminate and move forward. There is no way to do that. Plus, that won't work with infinite streams. You can have an infinite stream of dates, but there is no way you can filter anything out of that because it will be, well, evaluated infinitely. And if we actually put a pick method over there, you can see that, I hope you can see this. Actually, we could have dropped the whole processing after, let's say, 3 elements. But after this, we keep evaluating elements, which is not ideal, right? Well, it's not a tragedy, it works, but we could save some CPU cycles on that. And the solution for this? Well, you can either drop Stream API and rewrite everything using imperative looping, or migrate to JDK9, because this is where you actually get a dedicated method for this kind of things, which is called take while or drop while, which has this short-circuiting filter semantics. And now, if you want to switch straight from the old approach to the new one, you just replace the filter with take while, and then the stream will terminate as soon as the first mismatch is encountered. Very easy, right? Well, you probably expected something more spectacular from the talk that's called The Dark Side of Java 8. Don't worry, it's coming. So one of the biggest sins for me of the Java 8 is the issue of the stream flatMap, which was promised to be lazy, but actually is not. To give you a short, this is not another introduction to Streams API, but to give you a small, at least a bit of context, you need to remember that streams are not collections. This is more like, this is a concept borrowed from the world of functional programming that's kind of inspired by the idea of lazy sequences, where basically you don't store all elements eagerly, but you pull them out and whenever they are actually needed. And this approach allows you to achieve, well, be as performant as their imperative equivalents, at least in theory. Because the argument that I kept hearing a lot around 2014 was that the Stream API is really cool because, well, we can leverage the declarative approach, but Grzegorz, look how much waste is there. I'll try to point to both screens. So first, you need to take all users over there. Then you just flatMap all and take all addresses. That's a lot of operations. Then you filter, only to take just a single element. Well, that's a lot of waste, right? Because you could just take, if you were looping, you would just take first element and then return it. End of story. And you have lazy semantics out of the box, right? And the whole idea that streams are lazy, the whole idea of lazy sequences is to make them equal, because they will be processed vertically and not, well, horizontally as shown before. So what happens here is you get first user, you flatMap it with first address, you perform as many filtering as needed, and then only to take the final element over there. Well, this is what should be happening in practice. I mean, what should be happening, but it's not. So let's do a very short experiment. Let's take a list of users, and let's say that each user can be assigned to multiple addresses. And our job is to take a first address of the first encountered user. So, as you can see, we have a list of users with another list inside over there. Well, and it's a very easy task, right? Declaratively, you can just, well, take all users. You can flatMap each user with a list of addresses, and then take the first one, right? As easy as it is. And this should actually, and how this should look like. I mean, the evaluation of this. The stream should take the first element, first user, take the first address, and return it, right? You agree? Okay. So let's actually see what's happening inside. And we can do this using the pick method, which actually acts upon all elements that go through streams themselves. And now, if we try to evaluate something like this, we see that the stream actually consumed all the elements, although we wanted to get only one. And this is a huge issue, because suddenly it turns out that operations like this don't work with infinite streams. But the performance implication, well, is one bad thing, but it can also lead to very bad results. So let's take this very simple scenario. Imagine that the operation of get all addresses produces a very big or potentially even infinite stream. That could be especially true if you're working in like reactive kind of scenarios. And this kind of operation, if you were to judge the time complexity, would be usually O1, right? Because we take first element of an infinite stream, and we just take the first one. And this should complete immediately. Even if you were running on epsilon GC, which is a no-op GC, it should complete like this. And if you try to profile and see what's going on, actually you see the JVM underneath crying. So this is terrible news. But this is just performance. It will not work with infinite streams. But we don't use infinite streams that often. But what we do a bit more often is, for example, use flatMap with conjunction with another map operation. And now it becomes really bad, because look, we take only one element, but all those maps along the way are called the number of times that is the size of, let's say, this nested list over there. Not bad. So if some of you, let's say, perform side effects inside a map operation, well, you shouldn't, but you might, it's very bad, because imagine that you have an email sending logic over there. Well, good luck. Emails were sent to each address over there. So this is not very nice. And the cause of it is, if we look deep down inside how the Stream API is implemented, there's one method that's responsible for this. Let's actually zoom in. If you have a look at how the flatMap operation is implemented, you can see that deep down inside there is this for each, which is eager. This is an eager for each. And whenever you flatmap something and short circuit, it will always be the case that you will go through all elements. And this is super important to be aware of. By the way, if you thought that you can just put parallel streams everywhere and it will be super fast and parallel, well, as you can see, they will be serialized over there, okay, linearized. So how do we solve this? Well, we can implement our own split iterator-based lazy flatmap, which is doable, but kind of exhausting exercise. But the practical solution would be to migrate to JDK 10. Well, the bug has been actually identified a long time ago, around JDK 8 times. But there was certain argument if this is a bug or not. Well, technically it wasn't. No one promised that flatmap would be lazy. Well, the whole world makes it lazy, but indeed no one promised that. But in JDK 10 we got even more methods that would not work that nice along flatmap. So if you're on JDK 8, you can't do anything about this. You need to either write your own split iterators, you go back to looping. JDK 9 the same. But if you are on JDK 11, all good for you. So you don't need to worry about this, and you will consider this presentation interesting. But I think that for most of you that are on JDK 8, this is obligatory. And now, this is where the fun starts. As the first point today, we introduced the take while, drop while as a short-circuiting filter operation. And, well, it turns out that it behaves really weird if you put it along a flatmap. Let's have a look. So let's do a very quick test. Let's say we have two nested lists. So there's a list containing other lists. First list has only 1, 2, and second has 3, 4, 5, 6, 7. Very simple operation. We try to squeeze them together into one list. What will happen? So can you tell me? We have two lists, 1, 2, 3, 4, 5, 6, 7. We flatmap them together and print out. What do we get? 1, 2, 3, 4, 5, 6, 7. Perfect. Yeah, this is what sane people would expect from such code to how such code to evaluate. So let's start over, but from a bit different side. Let's take a stream of 1, 2, 3, 4, 5, 6, 7. Let's try to use the take while operation that we learned a few minutes ago, and print out all the numbers. So the current semantics are go through the whole stream, and when you encounter a 4, stop processing it. So what do we get here if we try to evaluate this? 1, 2, 3. Perfect, yes. This is sane to expect. We have 1, 2, 3, 4, 5, 6, 7. If we take elements while they are not a 4, well, we end up with 1, 2, 3. Yeah, as simple as that. But let's mash those two together. What do you think this will return? Come on, it's an easy example. Okay, we just did those two, right? We did the flatmap and then we did the take while. What do you think this will print out? 1, 2, 3, no? I can hint you that it's not 1, 2, 3, 4, 5, 6, 7 as well. Okay, it's 1, 2, 3, 5, 6, 7. And yes, and this is a real case. This is what's been happening in JDK 9. If you don't believe me, try it yourself. So this is so the problem with flatMap wasn't considered a bug in the past. Well, because it was just a problem with, let's say, performance or unnecessary computations. But once new short-circuiting operations were added to the API, it turned out it's totally broken. And unfortunately, well, the Stream API was promised to be so breakthrough, and it turned out that it featured a lot of small bugs that were that kind of spoiled the whole experience. But again, the practical solution to that problem, well, you can go back to looping, but you probably don't want that. So the practical solution is to migrate to JDK 10+, because finally it was identified and shipped. But no one really spoke about this because JDK 10 was about local variable type inference. So it's very important to be aware that something like this exists. Let's move further a bit from, well, bugs and flaws in JDK, and let's talk a bit about lambda expressions versus checked exceptions. If you've been working in Java 8 for a while, you probably already know what do you expect to see here. So actually, I really like how they implemented lambda expressions in a backwards compatible manner based on single abstract method interfaces. But there's a problem with this approach. So if you have a look at all interfaces that are shipped with Java util function package, you can see that there is this method apply over there. But it's missing one thing here. It's missing any possible throws clause. Well, it was a conscious choice, but it yields certain, well, let's say, inconveniences in the future. So whenever you call a method from within a lambda body, and you use those functional interfaces, you end up with this ugly situation where you need to actually try catch all exceptions all over there. And imagine that you have a very long Stream API chain, and you possibly don't care about exceptions being thrown somewhere along the way. You probably care if the whole Stream API throws an exception or not. So, well, we're promised for this functional declarative code to be really concise and readable, but we end up with monstrosities like this. Actually, a long time ago, I wrote a very small project that became surprisingly popular. That's just a collection of unchecked wrappers for the Stream API. This is literally the same as here, just packaged in a nice way. So it's not an ideal solution, but something that makes your code a bit more, gives you a bit more, let's say, aesthetics. But now, remember, not that long time ago, let's call them Oracle lawyers, were trying to convince us that the problem with the flatMap not being lazy is not really a problem, it's not a bug. And they were, well, technically they were right. So let's kind of try to reverse the dependency and try to play with, let's pretend we are, lawyers themselves. So if you go through JLS, through Java language specification, in section 18, there's a very interesting addition added in JDK 8, which means a bound of the form throws alpha is purely informational. It directs resolution to optimize the instantiation of alpha so that, if possible, it is not a checked exception type. This is from a section from generics. So it's very important information because this pretty much translates that whenever you use generics, every t in t extends throwable or exception will be inferred to be actually a runtime exception. This is supposed to help, for example, in kind of tricky scenarios, for example, like inferring a checked exception type from an empty lambda body. But let's actually try to use this information for our own advantage. So let's try to implement a very small method called rethrow. Well, we take an exception and we throw it, okay? No magic there. Let's try to make it a generic one. Okay, so we have now a static, let's say, method generified using the T that extends exception, and we rethrow it. Well, it doesn't work. Not good, but, well, because in this case we know that exception is an exception type, and it needs to be handled. And types don't really match. So what do we do if two random objects don't match? Their objects don't match. What do? We cast it, okay? So we cast it, and suddenly it works. The rule kicks in. It tries to cast it to a T, which is a generic type, and gets resolved a runtime exception. And apparently now, if you use this method, you can legally rethrow checked exceptions. And this pattern is called sneaky throws. It's been around for quite a while, although in the past it was achieved in a bit different way. So if we could put that in practice, well, let's create our own interface that's called, let's say, throwing function. And this is exactly like a function interface known from the Java util function, just with this throws exception over there. So now we will be able to actually represent methods lambdas that throw exceptions. So if we define a function, let's say a static helper method like sneaky, that's accepting those throwing functions, but returning old functions, well, we essentially have an adapter from the function that throws exceptions to the function that doesn't. Well, but now we have this method called sneaky throw that we developed like a minute ago. So we can implement this method by, well, pretty much wrapping the old method call, catch the exception, and then sneaky rethrow it. And at that point, compiler doesn't notice anymore that this is a checked exception. It's not perfect. Well, technically it's legal, but you need to be careful with that. Also, I'm aware that I might have gone really quickly through that. So if you want to read more about the whole idea, well, there will be something you have references. You can read more about this when you get the slides. So it's very important to stress out that you need to be very careful with that, because there might be problems with proxies. You might have another problems because if the compiler doesn't see that you throw a checked exception, then you can't properly catch it. Because if you try to catch this particular exception that's a checked exception, compiler will tell you, hey, it's not needed because, well, you are not throwing any. So be careful with that. Let's talk for a while now about parallel streams, which was possibly my biggest disappointment from the Java 8 world. Parallel streams were one of the biggest things of the Java 8 release. Streams were, well, they were leveraging declarative approach. And once you do stuff declaratively, you can do a lot of magic underneath. Well, just like, for example, databases do. So we were promised that once the stream API is there, we will be able to easily parallelize everything that we want. And forget concurrency, forget parallel computing. You just have streams API. You can call one method.parallel and, well, benefit from infinite performance. But is it really that easy? It turns out that don't. So the idea was to have such simple examples being able to easily turn into parallel ones just by adding one word, right? Infinite benefit. So if this is that easy, well, let's just replace all .streams with .parallel streams, right? Why not? Why not? But it turns out it's not a very good idea. So usually, if you try to parallelize operations by yourself, you would need to figure out a few different things. So you would need to probably pick which thread pool do you want to use. You would need to set it up properly, which means like minimal size, maximum size, what working queue do you want, what rejected execution handler, your own custom thread factory, and so on and so on. Usually that involved quite a lot of setup. But here you don't need to do anything. It's just well.parallel, bah, infinite performance. So some questions arise. So firstly, where are those tasks run? Okay, because if you want to have something run in parallel, it needs to run on something, on some thread pool, but we are not providing any, and there is no way to provide any. So what happens? Is it running in the cloud, in the blockchain? So one of the most basic operations that you want to do is, for example, provide your custom thread pool. Because, for example, imagine if there is one pool somewhere over there, and for example, if you submit a long-running tasks there, especially blocking ones, you might actually cripple the whole thread pool and all other tasks that are running on it. So a good rule of thumb is to actually make sure that you introduce separate thread pools for different tasks that are getting run in parallel to achieve some form of resiliency. You don't want everything to be run on one single thread pool and be coupled through that and to be able to impact each other. But it turns out that this is the case. Also, another thing to ask you is like, how many tasks can be run in parallel? I mean, it's like infinite 5 or what? Anyway, if we try to inspect what's happening in the spiral streams, you can figure out that they actually rely on the static shared fork join pool. First things first is that it's an implementation detail. There is no contract binding, let's say, the Java creators from actually changing it at any point in time. So technically, the thread pool that we use for execution of parallel streams is unspecified. There's a problem with fork join pool because it works really nice with CPU-bound tasks. It, for example, powers the whole akka, if you heard about it. But it's not the best choice for running blocking I/O operations, at least without using a managed blocker. But there's no way to really use that in parallel streams. But putting this aside, we know already that parallel streams leverage fork join pool, and you really want to run tasks on your own thread pool. Well, there's a hack you can use, because if you read the documentation of the fork join pool and the fork method, you can figure out that actually, if you call this method from within a pool that you want, it will essentially get hijacked. And this is what you can actually use in Java 8, and this has been one of the recommended hacks to do. But there's a problem, because in JDK 8 and 9, there was a very serious bug. So even if you thought that you are very smart, that you tricked everyone regarding looked at implementation details of Stream API and submitted, let's say, Streams API to be processed in your own fork join pool, then it doesn't work. Well, it seems to work, but at the end of the day, the size of the computation will be in proportion to the common pool and not the custom pool. So imagine that you have a very big, your common pool is getting very, let's say it has a huge, let's say, parallelism setup. But you want to have a separate pool, which has only a very small one. Then it won't work, because it will all leverage only, it will default to the shared one. But luckily it was fixed in JDK 10, so those of you that migrated don't need to worry about this. But if you can, just don't use this hack at all. But if you really need to, there are certain settings that you can, let's say, set through when creating your own custom fork join pool. It's like parallelism level, fork join worker, thread factory, uncaught exception handler, and async mode. I don't really know what async mode does. But since JDK 9, a very small upgrade was rolled out. Okay? Finally, you can tune the fork join pool properly using many more parameters. And this is really cool. But again, JDK 9 was about modules and not about small new constructors to relatively unused commercially APIs. But again, if you leverage those, remember that those hacks, those are essentially hacks that base on implementation details. So don't break a leg. And for the very end of this section, I'd like to remind you that it's always better to follow up on the cause of the problem. Let's say you are experiencing problems with database. Let's say that queries are too slow. Well, you can parallelize a few queries, run them in parallel, but then you will, well, let's say that it's not very, the common sense would tell you to leverage natural batching of databases that will parallelize stuff for yourself if possible. There is no need to hammer the database, move multiple connections in parallel. Same possibly with REST resources. Whenever you need to reach, let's say call n endpoints, probably it would make sense to just consolidate them and provide a separate API method directly for that. So in such cases, always consider parallelism as a form of, let's say, last resort. Often, parallelism will turn out to be not as performant as you might think. It's always important to benchmark this and see if the benefit is bigger than the starting point. So imagine a very simple scenario. You have, let's say, stream processing in parallel, something based on a new random object. It turns out that the sequential one will be faster than parallel. Why is this? Look inside and see how it leverages concepts from log-free programming and compare and swap. This can be much slower when multiple threads reuse the same object at once. So remember, be responsible when you use that. One of the last examples for today is a misuse of stream generate method. If you never used it, here are the docs. Stream generate returns an infinite unordered stream where each element is generated by the provided supplier. So for example, it's a very handy method that you can use for, generating infinite streams. And it works really nice. So you go for stream generate, you pass your own supplier, which returns certain numbers or certain values infinitely, and then you process it. Perfect. Will work really nice with random values as well. But let's say I want to do some stateful operations with that. Let's say I want to have, a monotonically increasing sequence from 0 to 100. Well, I write new supplier, I store the result somewhere inside, I increment it, I limit it for each, and bam, it works. Well, but let's say that I want to start doing the processing in parallel. Okay? And what do I get? Oh, wow, that's unexpected. But what's wrong with there? Can you tell me? I don't hear? 9 results? Not 9 results, but what's wrong with the implementation? It should be ordered, but suddenly everything is out of that. Yes, there is a problem with, simply put, thread safety. Because if you have the supplier, with some state, called from multiple threads, and not being thread safe, that will result in some undefined behavior. So let's fix it, and let's use atomic integer. All is good, all is thread safe, we run it again, and it's almost correct, because 1, 2, 3, 4, 5, 7, 6, something gets wrong. Okay, but it's thread safe. It might not be thread safe, but for the sake of this exercise, let's assume that it's thread safe. But it doesn't work. Let's actually add the pick method and see what's going on inside. Whoa, actually, I requested here only 4 elements, but got a lot of them going through the stream itself. But the result to be okay, it's 4 elements. The answer is that if you use stream generate and parallel streams, if the processing gets split into, let's say, a few different subgroups, it's very possible that each of these subgroups will progress beyond the limit that we set globally. So once the Stream API figures out that we are over the limit, we already processed more than those 4 required elements. But once merging them together, it happens to be, processed correctly, and we take only 4. But what's the problem with that? I've seen articles that actually showed this way of doing things. The problem is that we should probably read our documentations properly. It's a very common mistake, and it turns out that the documentation states that it always needs to be it's an unordered stream. So it's not a problem with thread safety, because you can achieve the same, let's say sequential, stateful operations like this using stream iterate. The problem is that this method doesn't guarantee you this at all. So all those results and all those behaviors are perfectly fine, regardless of the fact if we have a thread-safe or not thread-safe operation. So it's very important to remember about this because I've seen this mistake done a lot. And the last thing, very last thing for today is the optional versus option optional versus, well, the rest of the world. So I don't really know if this is true or not, but I heard a gossip that optional is called an optional and not option. Well, because it wasn't supposed to mimic an option. It was something, well, option-like, optional. And there is one difference, one very important thing that you need to remember that makes it, well, differentiates it from the rest of the world. It's the way it handles nulls. Imagine if it's a very simple scenario. You take an user, you use a map method, take its address, and then print it out if it's present. The problem is there that the Java version of option, it interprets nulls as, well, empty optionals. And you might be thinking that, well, it's fine because, well, no, we wanted to avoid nulls and optional is empty is a replacement for nulls. And yes, this would be true if we were able to remove nulls from the whole language. Then it would be totally true. But since the null is a perfectly valid value in Java, interpreting it in this way can be quite harmful because it might surprise you in scenarios, for example, like this one. Technically, if you have, let's say you have stream sequence, you have, let's say, multiple map operations. Technically, you should be able to move this from here to here, you know, from stream to optional, and nothing should happen. But this actually yields totally different results. So it's very important to be aware of. And you might laugh if you see like a sum with null in Scala. But this makes a lot of sense because, well, that's the whole world works, and this is how you not break monadic laws, actually. So this is how we are arriving at the end of this presentation. And you might be thinking that I've been like ranting a lot about Java, so the conclusion would be, I don't know, go to Kotlin or Scala. But actually my message for today was that it's actually worth paying attention to what's happening with those small things coming to Java. It's a very good idea to, from time to time, to at least screen the list of bugs that got fixed or the new APIs that are appearing. This is very beneficial. And the last thing for today, well, also, remember to read the documentation. Thank you. We have 2 minutes for questions. You can always catch me after the talk.
Raz. Hi. Has a study like that been done for the alternative languages? If we look at things like Kotlin or Scala, you know, given how much Java is used compared to, say, Kotlin, Kotlin must be full of this, right? Just empirically.
Can you say louder? I barely hear you.
I'm sorry. Has a similar study been done for languages that are less common than Java? Let's say Kotlin.
What do you mean similar study?
Yeah, well, looking into the problems of the respective stream API.
I'm not really sure if something like this has been done. Personally, I haven't done this, although I'm collecting a small, let's say, interesting bits that I can find all over the place. The only thing that if I could tell you right now, for example, from Kotlin, is that be very aware, be very careful when using, let's say, the optional types with Java tools. Because, for example, if some, let's say, I think it's the case with JSON and other tools that leverage on some misc and save, they can bypass the types, the null safety of Kotlin. So this is something that to be aware of. But I don't have any specific like bugs and points to point out here. Well, Scala have a lot of them, but. Okay, thank you.